All right, good morning students. We have so far we have covered many topics, and it is probably very clear to you that we need a lot of matrix theory for our course throughout. So, control theory, modern control theory especially demands a lot of matrix theory concepts, and hence I thought we will review some of these matrix theory concepts in a couple of lectures actually. So, now we will proceed with this basic concept in this lecture, followed by some of this slightly advanced concept in the next one, and then move on from there actually. So, what is basic definition for a matrix is essentially nothing but a collection of elements and typically numbers arranged in rows and columns. It is very standard, and I think all of you probably know this. So, if it is a various ways you can arrange the numbers, you can either arrange it in just a row or just a column or a combination of rows and columns. Okay. So, if it is just a row, it is a matrix also. Any single element is also a matrix, one by one matrix, but here we have something like a row vector, and this is what is called a column vector also. Okay. And then this is like a 2 by 3 matrix, and this is a 3 by 2 matrix, and here is a 3 by 3 matrix, like that actually. So, depending on how many rows and columns you have, you can also give something like a suffix here, I mean this 1 by 3 sort of thing here, and then 3 by 3 here and all, but these are not required because it is very implicit from matrix dimension actually. So, implicitly we just take it for granted actually. So, you may not be able to write this subscript all the time actually, you need not do that. And then some further definition, we call a symmetric matrix. A matrix is symmetric if it satisfies A is equal to A transpose. That is, if you take a transpose of the matrix, what is transpose by the way? This if you exchange rows to columns, okay, and then columns to rows, then it becomes like a transpose. For example, if it is C here, and then if you really take C transpose, then 1 2 3 will be down, okay, and then 4 5 6 will be next to each other, next to that. So, that is what is called, let us say if you if you do C transpose for example, then this will be something like 1 2 3 here, and then 4 5 6 there, that is C transpose. Now, obviously, we cannot talk A equal to A transpose, A equal to A transpose, unless A is a square matrix actually. Okay. So, we need A to be a square matrix before we talk about A equal to A transpose, but all square matrix need not be symmetric either. Okay. It has to satisfy this property for a matrix to be symmetric, and especially if you see this particular matrix, okay, and obviously it is not it is actually a symmetric matrix, because you see this element is coming here, okay, 1 2 element is actually 2 1 element, and this element is also here, and this element is also there. Okay. So, E is actually a symmetric matrix that way. All right. Now, there is some concept called singular matrix, and singularity means the determinant has to be 0. Okay. And these concepts come from inverse definition also, because inverse is defined as adjoint of A divided by determinant of A. So, if the determinant is 0, then A inverse tends to go to infinity actually. Okay. So, singular matrix is a matrix for which the determinant is 0. Now, what is the inverse of a matrix? That is the next concept. Okay. The definition wise, matrix B is an inverse of matrix A if, this means if and only if A times B is equal to B times A is equal to identity. So, if that happens, then B and A are inverse of each other actually. Okay. And inverse of A is typically given by this formula, but this serves as a definition actually. AB equal to B equal to I is the definition, and A inverse happens to be adjoint of A by determinant of A. I am very sure you know what is adjoint of A. You have to find out the minors cofactor and then make some transpose and all that actually. So, I think that is known to all of you. Now, the next concept is what is called as orthogonal matrix, and orthogonal matrix is a matrix for which you satisfy this property, A times A transpose is equal to A transpose times A is equal to I. What is the beauty of that? Now, correlate that with this inverse matrix definition, you will find that A inverse is nothing but A transpose. It is a very beautiful property, but you do not have to do so much of operation unnecessarily. This orthogonal matrix, inverse happens to be just the transpose actually. And then okay, what is an example for that? If you have a this kind of a matrix, okay, cos theta and minus sin theta out here, then you can very clearly see that if I just take a transpose of that, okay, very quickly probably you can do that here, okay, that let us see T transpose, okay, is okay, is something like cos theta out here, and then it is like sin theta minus sin theta out here, that is row going column and column going row basically. Then if you multiply this together, okay, this A matrix, this T and T transpose if you multiply together, okay, then you will get cos theta times cos theta, that is cos square theta, okay, and then it will get that cos theta sin theta and minus sin theta cos theta will cancel out. So, what will happen here is like T times, okay, sorry for that, the T times T transpose, if you do that, it will happen T times T transpose is something like 1 here and 0 here, 0 here, that is nothing but identity actually. Okay. So, that is why this matrix is actually a orthogonal matrix out here. Okay. And also you can see that this particular example is very clear that if a matrix is orthogonal, then the columns are orthonormal to each other. The columns are vectors and it is orthonormal. Orthonormal is what? X and y vectors x and y are orthonormal, okay, provided the inner product between them is actually 0, and then magnitude of x and the magnitude of y, okay, is both 1 actually. Okay. And you can see that because cos square theta and okay, if you have this property, then cos square theta plus sin square theta, okay, is equal to 1, and it also happens to be the same thing for column 2. And then if you take x, I mean inner product of that, cos theta into negative sin theta, that is minus sin theta cos theta plus sin theta cos theta, that happens to be 0. So, inner product is 0 and the magnitude of each column is equal to 1 actually. So, magnitude or inner product being 0, they are orthogonal to each other, and magnitude being 1, in addition to the orthogonality, it will call that as orthonormal vectors actually. So, if a matrix is orthogonal, then the columns are they are orthonormal to each other. So, that is a property that we should keep it in mind actually. And by the way, this matrix that you see here is also a very neat matrix. It is what is called as rotational matrix actually. Okay. So, if you have for example, if you have a coordinate frame, okay, if you have a coordinate frame something like this, and they have a point here, okay, point P let us say, and you have some coordinate in this x and y. Okay. Now, the question is, suppose I rotate this coordinate frame by angle theta, okay, this coordinate by angle theta, then what is the same coordinate in this new coordinate frame? Okay. So, that property is related to this matrix that you see here. In other words, the same coordinate in the new coordinate frame will be this matrix times the old coordinate actually. Okay. So, you will get the new coordinate. It is rather fairly easy to derive that also actually. Alright. So, we will proceed further, and then the next concept that we require heavily in control theory is the concept of eigenvalues and eigenvectors. Okay. Before we know this in little more detail, we also realize that matrices are also linear operators. Okay. Any matrix numbers what you arrange them, they also serve as linear operator, and that is a property of stretching and rotation as well actually. What do we mean by that? So, let us operate this matrix A with respect to a vector P starting from origin, let us say, which has coordinate x1 and x2. Okay. If I have some point P which is given by a vector from origin to P, that is coordinate x1 and x2, I multiply that with A, then I will get y1 and y2, for which I will get a point Q let us say. Okay, because y1 and y2 can be very different from x1 and x2. So, in that sense this vector what you see here and this vector what you see there are different in both magnitude as well as direction basically. Okay. So, that means this particular matrix serves as both stretching operation because the vector lengths are different, as well as a rotational property because the directions are also different actually. Okay. Now, then we naturally ask a question that does there exist some combination of some vector with respect to this particular matrix for which it can only act as a stretching operator. there is no rotation actually. Okay. If I take this vector x and then multiply with this matrix A, then I will get some other point, but that will be only a stretching operation, not a rotation operation actually. Okay. So, those direction, whatever direction pops up, that is called eigenvector direction or principal axis and things like that actually. Okay. So, those are the direction that are given by eigenvectors essentially, and the magnitude of stretching is actually eigenvalues. Okay. And there is in general this operation, this magnitude can be complex number and things like that actually. Okay. So, we will not venture too much into that, but then you say that okay, we are searching a particular vector x with respect to that particular matrix A that we have. So, that this linear operator applied with respect to that vector will give me another vector with only stretching operation, no rotation actually. Okay. So, that is the eigenvector direction, and the amount of stretching is nothing but eigenvalues. Now, relying on this philosophy, what does the math says now actually? Okay. How do you operate that? So, what is the question? Question is, can we find a direction or a vector along which the matrix will act only as a stretching operator? And answer to that is, if that happens, then what is that? It is a stretching operator anyway, right. So, Ax, whatever Ax is, that is nothing but lambda times x. So, lambda is just a scalar quantity now. Okay. Ax is equal to lambda x will give us the only stretching operator actually. That is what we are talking here, Ax equal to lambda x, and if that happens, then I can take this one to the right hand side, and then it will tell okay, this is lambda I minus a into x, because remember lambda is a scalar, but we are talking about a vector and matrix operation here. So, it took lambda times I actually. So, lambda I minus a equal to g times x equal to 0. So, if that happens, okay, then if this equation is true for a non-trivial solution for x, that means this equation is anyway true for x equal to 0, but we are not interested in that, we are not interested in a origin point actually, we want a direction actually anyway. So, for a non-trivial solution, this will have a solution provided this matrix, the coefficient matrix is singular. Okay. And you may have infinite solutions by the way. Okay. If the matrix, the coefficient goes singular, then you can have actually infinite solution, because rank of the matrix reduces in that sense actually. But anyway, coming back to that, this non-trivial solution requires that we have this determinant equal to 0, and that is how we typically see in undergraduate texts and all that, that we deal with this equation commonly called characteristic equation anyway, right. So, given a problem, we directly can jump into this equation lambda I minus a determinant equal to 0 and try to formulate a polynomial in lambda if A is n by n. Remember, all these are nicely defined for square matrices actually. Okay. For non-square matrices, eigenvalues, eigenvectors are not defined. So, lambda I minus a is also a square matrix, and you take a determinant if A is n by n, then this polynomial will be nth order polynomial. Okay. So, we will give something like a n values for lambda, they may be repeated, they may not be repeated, they can be partly repeated, partly non-repeated, they can be partly complex conjugate as well. Okay. Assuming that A contains only real values, then this characteristic equation can partly take complex conjugate solutions as well actually. And then whatever corresponding x that pops up, okay, that is common, that is known as eigenvectors. Okay. So, the solution for each of the solutions actually, for each of the solutions of lambda, we will get a corresponding x, and that will give us the corresponding eigenvalue eigenvector pair actually. Okay. So, in other words, going back to that diagram, there need not be only one direction, then can be multiple directions actually, for which this equation is satisfied, and then that will be given by this equation, and you will have n such pairs eigenvalue eigenvectors actually coming out of these two equations. And also remember that eigenvectors do not have a specific magnitude per se, because the moment this is the determinant is 0, you have infinite solutions for x. So, any value, any particular vector is an eigenvector by definition. We really do not worry about the magnitude of eigenvector. Eigenvector is typically direction, but for our further discussion and all, normally we normalize the eigenvector. That means any eigenvector, we can take a normalized quantity and tell okay, that is my eigenvector actually. Okay. So, that is typically we do that way, but by definition eigenvectors do not have magnitude actually. So, where are the utility? Utility is heavily there in stability and control analysis and synthesis, that is why we are studying this. Is also there for model reduction, it will give you principal components and all, the insignificant components you can neglect, that will be coming out from the magnitude of eigenvalues actually. then you can, for example, if it is a symmetric matrix, we will see it later, that the eigenvalues are guaranteed to be real, and then you can arrange them in a descending order and things like that. Then you can truncate that spectrum and tell, okay, up to that I will take and beyond that I will neglect. That is, that kind of concept is called model reduction actually. Okay. This is also used for principal component analysis. That means, if your data is kind of scattered around and you want to find out the principal directions around which your data is scattered, and you want to neglect the other direction, things like that, there also you want to have something called principal component analysis, and there also eigenvalue, eigenvectors play a heavy role. So, they are there everywhere, they are there in stability control, they are there in model reduction, principal component analysis, stress vector analysis, the structural analysis, there are applications in fluid dynamics everywhere actually. Okay. So, but we are primarily interested because of stability and control properties embedded in that actually. Now, next terminology, next concept, what are called as positive definite, negative definite matrix, like that actually. Okay. So, a matrix is called positive definite, okay, provided this property holds good actually. Okay. Okay. That means, if you take any any vector which is a non-zero vector, and I do this algebra, that is x transpose A x, that is always guaranteed to be strictly positive. Okay. And this is obviously a scalar quantity, remember that, x transpose A x, and these are all for square matrices actually. Okay. So, if I take any square matrix and multiply with appropriate dimension vector x to the right and x transpose to the left, for any x I take, I do not care about that magnitude, as long as that is non-zero, I am guaranteed to get a positive number. Okay. That is called positive definite matrix, if that happens actually. And similarly, if it happens to be like greater than equal to 0, then it is called positive semi definite matrix, and similarly, if it is strictly less than 0, it is negative definite, and less than equal to 0, it is negative semi definite. And notation wise you can still write it, but this is simply a notation, remember that. Okay. Because A is a matrix and A greater than 0 does not mean each of the elements of A greater than 0, that is not the meaning actually. The meaning is in this sense. So, many of the analysis in control system, you can see that A is greater than 0, that means simply what it means is A is a positive definite matrix actually. Okay. In the meaning is like that, and it is a natural consequence that it is actually very tightly related to the eigenvalues. And if it is a positive definite matrix, it turns out that all the eigenvalues of this matrix are guaranteed to be positive numbers. Okay. So, if you have studied this definition from eigenvalue property point of view, my suggestion is these are not definition, these are all consequences actually, right. But sometimes they are also taken as definition, because these are if and only if results actually, it is not one sided results. Like if this happens, that is going to happen, and if this happens, that is also going to happen. So, sometimes these properties of eigenvalues and definition, they are kind of interchanged, but in strictly speaking these are definition and these are properties actually of those matrices. So, just remember that. Okay. So, now next we will study some of these useful properties of eigenvalues and eigenvectors. So, let us study one by one actually. So, what are you telling here? The first thing is if lambda 1 to lambda n are eigenvalues of a matrix n by n, then for any positive integer m, these powers of these eigenvalues are also eigenvalues of this a to the power m. It is a very beautiful property in that sense, because if I know the eigenvalues of a matrix, I really do not have to compute for a square, a cube, a 3, a 4th, all sort of things actually. I can simply take their powers and I will directly get the eigenvalues of that. It is rather easy to show also. Let us show that in a very quick way. So, you have a lambda as an eigenvalue. So, you have your equation is satisfied this way. This is by definition anyway. Okay. So, I want to show that lambda square is an eigenvalue for a square, and then you can generalize that for a q, a 4th and all that actually. So, for that what I will do, I will just pre multiply both sides by a. Okay. So, I get a times lambda x. Remember, vector matrix is this pre multiplication and post multiplication is to be done carefully. So, then this one is a square into x. However, lambda is a scalar quantity. So, I can take it outside that, and then lambda into a x, that I will get, and then this is a x is equal to lambda x. So, I will take this is nothing but lambda x, and hence it is lambda square x. So, what I am getting here, a square x is nothing but lambda square x. So, obviously by definition again what you get it here, this tells me that lambda square is nothing but an eigenvalue for A square. That tells me very clearly actually about that. Okay. So, what you get here. Okay. So, this x equal lambda x, so the similar expression is there. Now, if you multiply one more time here, okay, this equation you pre-multiply one more time, you get a q x is still lambda q times x. So, like that you can continue, okay, and then tell, okay, for any integer power I will get lambda to the power m is actually an eigenvalue for a to the power m. And beautiful thing is as a consequence or as a corollary, eigenvectors remain same, because you see that same x appears here, same x appears here. So, eigenvalues will take their powers and eigenvectors will remain same actually. Okay. So, that is a nice property. Now, the similar thing is also true for minus 1 as well, and remember minus 1 means inverse actually, a to the power minus 1, that means A inverse. So, if I know the eigenvalues of A matrix, then all that I have to do is 1 by lambda 1, 1 by lambda 2, all that I can take and then claim that these are actually eigenvalues for A inverse as well actually. So, how do I do that? That is also simple. Starting from this equation, okay, I will start from this equation and tell, okay, this time I will multiply with A inverse rather. So, I will get A x equal to, I mean A inverse into A x is equal to A inverse lambda x. So, if I do the simplification, A inverse into A is identity. So, I times x is equal to lambda times A inverse of x, and identity x is I times x is x obviously. So, what I get? I will get 1 by lambda times, okay, x, okay, is equal to 1 by lambda times x is nothing but A inverse x. So, the same equation, if you just rewrite the left side into right side into left side, what you are getting? A inverse x is actually 1 by lambda times x. So, this equation tells us that 1 by lambda is an eigenvalue for A inverse actually. Okay. And again as a corollary, eigenvectors remain same. So, they are rather easy, I mean they are not difficult, even though the results are very powerful, the results are not very difficult to solve at all actually. Now, the third one, for a triangular matrix, the eigenvalues are diagonal elements. These are very clear from the definition itself actually. Okay. If you go back to the definition and tell, okay, this is what I have, suppose if I have a triangular matrix, then this equation is nothing but lambda minus the diagonal element 1, lambda minus the diagonal element 2, like that actually. So, okay, you can, if you want to just have a example. So, if I take let us say 1, 2, 3 and then let us say 2, I mean 0, 2, 3 and 0, 0, 3, let us say something like this matrix, then the characteristic equation is lambda I minus A, okay, determinant actually, okay, and that polynomial will give me lambda minus 1 into lambda minus 2 into lambda minus 3, and if I equate it to 0, then all that I get lambda 1 is 1, lambda 2 is 2 and lambda 3 is 3. So, the characteristic equation only diagonal elements will pop up actually, other things will not appear. So, that is that is why it is more powerful actually. Anyway, so that is the result why it is why I tell that, okay, for a triangular matrix the eigenvalues are diagonal elements, and as a I mean it is very clear that diagonal matrix is also a triangular matrix, and hence for diagonal matrix the eigenvalues are nothing but diagonal elements actually. Okay. Now, the next big property which is very useful to us is something like this, which tells us that if a square matrix is symmetric, then the eigenvalues are all going to be real. It is a very powerful result actually. If I know that a matrix is symmetric, then I am for sure I can say that eigenvalues are guaranteed to be real actually. Okay. So, the complex conjugate and other things will not appear, the eigenvalues are not going to be complex at all actually. Okay. Then on top of it, moreover, it will have n linearly independent eigenvectors as well. So, it is a very powerful result, and hence most of the time given a choice we would like to formulate a symmetric matrix. If we have to ever formulate a matrix, then typically we will formulate a symmetric matrix in our problem formulation actually. So, suppose a matrix is given to us, we do not have a choice, we have to work with whatever we have, but if it is even in that case we can actually talk about decomposing into that. So, something like suppose A is a non-square matrix, okay, then you can decompose that something like A plus A transpose by 2 plus A minus A transpose by 2 as well. Okay. This is supposed to be symmetric, this is supposed to be kind of a skew symmetric, what is called actually. Okay. So, this is still we want to do, because if this component is negligible, that means if the skew symmetric component part of it is not that significant, then we will still leave left out with an approximate matrix which is still symmetric matrix actually. So, that is a good property that you will have to exploit actually. And some of these proofs and all you can, if your time permits, you will see it in a class, otherwise you can read it from standard textbooks actually, that is also possible to do. And the next big property is if a square matrix has n real eigenvalues and n orthogonal eigenvectors, then the matrix is guaranteed to be symmetric as well. That means, this property is actually a converse of this property. So, whatever you see there, if a matrix is symmetric, then the eigenvalues are all going to be real and it has n linearly independent eigenvectors. Okay. Now, the converse property tells us that if a matrix has n eigenvalues and n real orthogonal eigenvectors, remember these are not necessarily linearly independent eigenvectors only, they have to be orthogonal as well. And if it has n orthogonal eigenvectors, then the matrix is guaranteed to be symmetric, that is the converse theorem actually. Now, the next property is what is very handy many times is, if you have a matrix something like A transpose A or A transpose, this is guaranteed to be positive semi definite always, and it is not that difficult to show it either actually. So, how do we show that? We will see if you have a matrix something like A transpose, okay, let me do that, or A transpose A either way, okay, then what you do, you multiply that with let us say x transpose and x actually, that is what you really want. Okay. So, okay, and then you can tell, okay, this is nothing but x transpose A into A transpose x, okay, and one is the transpose of the other. So, this is, suppose this is y, then this is supposed to be y transpose. So, and then this is nothing but, okay, this is equal to y transpose y, that means it is something like y1 square plus y2 square plus y3 square, like that actually. Okay. This particular quantity what you see here, y transpose y, is y1 square plus y2 square plus y3 square, all that, and that is guaranteed to be greater than equal to 0 actually. Okay. Okay. This particular thing is guaranteed to be greater than equal to 0 because of that property. Okay. So, that is why this is a positive semi definite actually. Okay. And you can show that for the other one also, if it is A transpose A, that is also easy to show that actually that way. Now, next property, if A is a positive definite symmetric matrix, okay, then every principal submatrix of A is also symmetric and positive definite. Okay. In particular, the diagonal elements of A are always guaranteed to be positive actually. So, this is also, remember that if it is a positive semi definite, positive definite matrix, then the diagonal elements are guaranteed to be positive because of this property. So, if you see a matrix where diagonal element, one of the diagonal matrix is negative, then you can right away tell that the matrix is not going to be positive definite. Okay. So, that is the consequence of that. Now, I will go to the next property, and this is some concept called generalized eigenvector actually. Okay. So, as you remember that okay, if you have independent eigenvalues, okay, like linearly independent eigenvalues, then you are guaranteed to get independent eigenvectors as well. So, non-repeated eigenvalues, what I mean. If you have non-repeated eigenvalues, then you are guaranteed to get linearly independent eigenvectors because of that property, right. Okay. Okay. Now, if you come back to that, then ask questions, okay, what if some of the eigenvalues are repeated actually, do we still guarantee that? Now, it turns out that if some of the eigenvalues are repeated, then you may or may not get independent eigenvectors actually. Okay. And if you get independent eigenvectors, that is well and good, and if you do not get independent eigenvectors, then you would like to have some vector which is actually rather close to eigenvectors. It may not be exactly eigenvector, but the properties may be very close to the eigenvector actually. Okay. And some precise definitions are also available for general eigenvectors, but in a way we want some eigenvector which is very close to the eigenvector in some way actually. Okay. how do you compute that? If you have, let us say you have lambda 1 and lambda 2, that means lambda 2 is repeated twice. Okay. Then for lambda 1 and lambda 2 you will get V 1 and V 2 anyway. So, that is fine, but for the third lambda 2, which is also same as the second lambda 2, you suppose there is no linear independent eigenvector, then you formulate this sort of an equation where the right hand side is not equal to 0, but it is equal to V 2 rather. Okay. So, then whatever solution you will get V 3, that will be like a generalized eigenvector set actually. That is not eigenvector truly speaking, but it is close to eigenvector in some sense, that if in a epsilon delta sense there is a limiting sense behavior and all that is available in Kailath book actually. If you want to see that, Thomas Kailath book, you can refer to that and tell that is the property that will satisfy. In a limiting sense it will become an eigenvector actually in a way. So, the equation that is needed to satisfy is like this actually, and also suppose this lambda 2 is repeated one more time, then what the next equation will be, this into V 4 is equal to V 3. So, this is V 3 is equal to V 2, the next one will be V 4 equal to V 3 here. Okay. That way you will compute V 1, V 2, V 3, V 4, part of them will be real eigenvectors and part of them will be generalized eigenvectors. And these eigenvalues eigenvector set are actually very useful in matrix transformations, especially similarity transformation. You will see that in the next class actually. The next concept what is useful to us is something called vector norm. Okay. So, what is a norm? Actually norm is a concept of a distance sort of thing, that means how big is a vector. Okay. Suppose you have a scalar value, we can really compare, one is smaller than the other, I mean the magnitude wise, one is lesser than the other quantity, one is bigger than the other quantity, like that actually. So, somewhat we also want to know what, in the vector sense, how much it really quantify. Okay. So, I mean one way to quantify is just Euclidean distance from origin, that is what we saw that in one of the slides before, that the length part of it actually. Okay. That is the Euclidean distance from origin actually. Okay. So, if you really take that distance, that is nothing but square root of x 1 square plus x 2 square, that is happens to be a second norm actually. Okay. And somebody can always argue that hold on a second, I will not do it that way, let me travel from origin to that point using this way, I will go this way first and then go that way, I will still cover some distance actually. So, this is parallel to x axis I will go and then parallel to y axis I will travel. So, if I just take the summation of this distance plus that distance, that happens to be what is called as L1 norm actually. Okay. That is also distance quantity by the way, that is also going to be a positive quantity, that also signifies how big is your vector, and that happens to be a norm quantity as well actually. So, like that you can define various ways, and the formal definition turns out to be something like this. Norm, vector norm is actually, remember it is a vector norm, that means it is defined for a vector, not for a matrix in general. Okay. So, x is a vector and the norm of that vector is a real valued function, that means actually it is the ultimate number, the norm is essentially a scalar number. Okay. That real valued function will satisfy these three properties actually. What is that? Norm of a vector is guaranteed to be a positive quantity, is never going to be a negative quantity as long as x is non-zero, and if x is 0, then the norm is guaranteed to be 0. That is the first property. So, if as long as it is a non-zero quantity, non-zero vector, that is you are moving away from origin in any direction, whatever direction is that, then the norm of that quantity is guaranteed to be a positive number, and it is very compatible to the distance traveled concept. So, no matter what direction you travel, the distance travelled is guaranteed to be a positive number anyway. So, that is kind of a similar thing there. Now, if you do a scalar multiplication of that vector, okay, and then take a norm of that, then it should satisfy the absolute value of that number into norm of that vector, that should satisfy that actually. Okay. Then quantity C, okay, that the property, third property, this is something called triangle inequality, and that tells me that if I add two vectors, okay, of similar dimension of course, and then I take a norm, that will satisfy a less than equal to property that way. Okay. No matter whatever is my x and y, no matter whatever is my x and whatever is my y, if I take them x plus y and then take a norm of that, then it is guaranteed to satisfy this less than equal to norm of x plus norm of y. So, any quantity, any function that you define for norm has to satisfy these three properties actually, right, and obviously satisfying these properties we can define these quantities actually. Okay. That if I simply define the absolute value of x 1 plus absolute value of x 2 plus absolute value all the way up to x n, then it will satisfy all these three properties anyway. Okay. Absolute values, all the absolute values are positive quantities. So, it is the summation of that is guaranteed to be positive quantity also. It is going to be 0 provided only if x is 0. So, that will satisfy from this definition. It will also get satisfied from all these definitions actually. Okay. And then or you can also verify that the rest of the two quantities are also satisfied. I mean they will also get satisfied with respect to all these definitions actually. And if you have only this formula, then it is something called L1 norm, and this formula is something called L2 norm, this formula is something called L3 norm, like that actually. You can define any order norm by the way. So, pth order norm LP norm is defined like that. So, you take absolute value of each of the quantity, raise it to the power p, take their summation, and I take pth root of all that actually. Okay. So, you take first raise to the power p, then take the sum and take pth root of that actually, positive pth root of that. Okay. So, then you will whatever quantity you will end up with, that is called pth norm actually. Okay. So, starting from 1 norm, 2nd norm, 3 norm, 4 norm, 5 norm, up to infinity norm we can define by the way. Then it so happens that the infinity norm also happens to be just that. If you simply take the maximum of that quantity, whatever quantity you are having x 1, x 2, all that thing, if you simply take maximum of that value, okay, that whatever component is the maximum one, okay, then that is nothing but infinity norm actually. So, if you go back to the diagram and say what is my infinity norm for vector 1, then obviously it is going to be absolute value of x 1, and for vector 2 it is going to be absolute value of y 2 basically. Okay. So, like that actually. So, typically in our analysis of control theory we will require L1 norm, L2 norm and infinity norm. Okay. We will all work along with these three lines only. Okay. And there is also a theorem which tells us a little later I will tell probably that in a finite dimensional vector space, okay, all norms are equivalent actually. They are not equal of course, but they share a equivalence property. What does that mean? If you show that the second norm is bounded, then all other norms will also get bounded actually. Okay. That need not happen in infinite dimensional vector space, but as long as finite dimensional vector space n is a finite number, then all norms are kind of equivalent actually. That theorem is a very handy tool which will tell us that okay, we will not have to worry about each of the terms individually, okay, each of the definitions actually. So, most of the time we will either deal with second norm, but you will see that all LQR theory, quadratic things, and then this kernel filter, all these things we will talk about H2 sort of an idea. Sometimes these are called H2 norms also. I mean H comes from Hardy space and all that actually. I will not go too much into that. And then either we deal heavily into 2 norm, or sometimes we like to deal with the maximum quantity of the noise and things like that. Okay, your system has to be stable for maximum noise magnitude that you expect actually, noise frequency and amplitude, all that actually. That concept is H infinity concept. So, for H2 concept control theory we will require the second norm, for H infinity concept we will require the infinity norm. So, mostly we will do with L2 norm or L infinity norm actually. But remember, as long as I show something, all the norms are actually equivalent actually. Alright, that next it throws to the natural question that okay, we discussed about vector norms here, what about matrices actually. Okay. That means even if I have a matrix, can I talk about how big is that matrix? Okay. And actually it is also related to how far I can stretch the vector actually, right, remember that. Suppose Ax, remember Ax is nothing but something like we have seen that in eigenvalue eigenvector, y equal to Ax, and then Ax, okay, well let me, okay, y equal to Ax, and also we have seen that this is this also serves as something like a stretching operator actually. Okay, we are not so much concerned about rotation here, let us say. Now, we will talk about stretching operator. Now, no matter whatever is my x, okay, this y, this a times x, I want to know how much this vector is getting stretched actually, getting elongated, how much it will go elongated actually. Okay. Then if I say okay, that property I want to extract, then let me extract it that way. I will take any vector that is non-zero, I will first formulate an A times x matrix that will give me a vector y, and that magnitude of vector y I will divide it by magnitude of vector x. So, whatever is that ratio, that magnitude of vector y divided by magnitude of vector x will give me a, certainly it will give me a positive quantity, positive number actually, okay. And that number is nothing but matrix norm actually, okay. And suppose to simplify my algebra, I consider something like I will constrain my norm x to 1, that means I will walk around that unit circle or unit ball or unit sphere, things like that on the surface of that. Then all the values of y that will pop up, I will take them and then find out what is the maximum value out of that, okay. So, it is the maximum stretching condition that comes into picture while defining what is called as matrix norm, which is also called as operator norm for obvious reasons. Matrix is a linear operator. It is also called as induced norm actually. So, there are three different norms for different names for the same thing actually. Anyway, so that is the idea. Idea is this matrix norm is nothing but a stretching operator. I want to extract how much it stretches with what vector and the maximum stretching what it can do in whatever direction, that is actually my matrix norm. Okay, so remember, if I take different x, the stretching can happen in a different magnitude basically. So, I am considering the maximum stretching out of that. So, what are the properties that it has to satisfy? Again you see that first three properties are very similar to what we have earlier, okay. First three properties are very similar to what we have earlier, but it also needs to satisfy some sort of a triangle inequality in multiplication sense as well, okay. Only addition is not sufficient. It will also satisfy something like a multiplicative inequality, which tells us that A times B norm is less than equal to norm A times norm B, okay. So, that is what will satisfy, and then definition wise is something defined like that. It tells okay what is this first one norm, two norm and infinity norm. Again as I told, these are the three quantities that will worry most of the time. And let us talk about okay, two norm, which is very popular, which is nothing but maximum singular value, and singular value is something that I will take you through, okay, in definition sense and all that. So, this if you take all singular values and find out the maximum singular value, that is nothing but the second norm actually. So, that is kind of obvious, fairly straightforward in that sense, as long as you find the singular values basically. Now, okay, what is one norm and second norm? These are defined something like that, mathematical notation wise they are like this, okay. However, English word sense, these are nothing but largest of the absolute column sums, and this is nothing but largest of the absolute row sums actually. So, what do you mean by that? Alright, so let us go to that and tell okay, there is a matrix out here, A matrix, there is all numbers actually spread out everywhere, okay. Now, what do? I take absolute values of all the terms actually, whatever values are there, okay. Okay. If once I take absolute values of that, then I can sum it up across rows, okay, all of them sum is, and I will get a number here, number here, number here, okay, and I will consider the biggest one here. Okay. Let us say this happens to be larger than first and third, then that happens to be an infinite norm, okay, because it is nothing but largest by definition it is nothing but largest absolute row sum actually, okay. Okay. Now, if I do the similar operation column wise, okay, if I can take this one and then find a number, this one and again this column wise find a number, okay, and find a number and tell okay, this is the maximum out of all that, and then that happens to be my largest absolute column sum, and that happens to be my one norm actually, okay. So, the one norm is nothing but largest absolute column sum, and the infinity norm happens to be largest absolute row sum. And it is rather easy to remember, why I do not have to get confused unnecessarily, because remember letter 1 is vertical and letter infinity is horizontal. The way you write letter infinity is horizontal and the way you write letter 1 is vertical. So, that is what it is very clear to see that way. Okay. Now, going to the induced norm, I mean there is also another concept called Frobenius norm, which is also useful in a lot of this matrix theory analysis, neural network analysis, all that, which is nothing but almost like a second norm for vectors actually. What you do vectors, all these you take square, add it up everywhere, and then just take summation of everything and then take square root of that, positive square root of that. And similar concept if you do, we just blindly just square up all the terms in the matrix and after taking all the squares you just add them together and then take the final quantity, you take square root of that. That will give you Frobenius norm actually. It will also satisfy this basic properties that you talk about, and hence it is also a norm. So, that particular thing is also used for neural network training and all. We will see some of the adaptive control, because none of the weights in the matrix you really want to go unbounded actually. Okay, this will satisfy certain nice properties actually. Now, the next concept which calls as spectral radius. Okay. So, the spectral radius is nothing but something like maximum of these absolute values of lambdas actually. Okay. So, if I take eigenvalues of a matrix n by n, and then simply take the absolute values of that eigenvalues. Remember, even if there is a complex eigenvalue, I can still talk about a magnitude of that quantity, that complex number, and then I will find out what is the maximum absolute value of that eigenvalue. Okay, that is nothing but the spectral radius of that matrix. So, eigenvalues, remember, they give the quantity, the magnitude of stretching basically. So, I want to know what is the maximum stretching that can happen also in a way. So, that is nothing but spectral radius actually. So, now a standard result tells us that spectral, there are two norms. Okay, two norm is related to the spectral radius that way. Okay, and if A is symmetric, if you talk about a symmetric matrix, then A2 is nothing but that, by definition. And if it is symmetric, you know A transpose is also A, that means it is A square. And then it will happen that this square and remember this after all is an eigenvalue actually, right. The property is related to eigenvalue, and eigenvalue of A square is eigenvalue of A to the power 2. We have seen that one of the properties. Okay, so, you can use that way and then come, this is what is going to be my spectral radius actually. So, the second norm is nothing but the spectral radius of the matrix also. Okay, so, that is very easy to show that. Alright, the last concept in this lecture probably we will talk about what is called as least square solution. Okay, and this least square solution is a concept which is very close to the like solving a system of equation actually. Okay, so, we are concentrating will very repeatedly we will come across this equation. Suppose I mean in a control theory, we will most of the time we will end up with something like a matrix, some B matrix, something is nothing to do with the control influence matrix, but some matrix times U is equal to some function actually, like some vector V. Okay. Now, how do you solve for control actually? Okay, that's the question that we will typically end up with many times in control design actually. So, we are generalizing that and tell, okay, this is the equation that is of primary importance to all, and then see what all possibilities can happen actually. And remember, x is a n dimensional vector and b is a m dimensional vector in general. That means, the number of equations are actually m, and the number of variables that you are talking about is n actually, they may or may not be same. So, obviously, it will arise three cases. Now, we will study case by case. Now, case 1 is something like we will concentrate m equal to n, then what happens? That means, number of variables are equal to the number of equations, and on top of that we are assuming the determinant of A is not equal to 0. Then the solution is very straightforward. We have seen that in many times, that is nothing but x equal to A inverse B. So, if you pre-multiply both sides by A inverse, if you start with A, the Ax equal to B. So, pre-multiply both sides by A inverse, Ax is equal to A inverse B. Okay. And then you tell, okay, this is nothing but identity. So, x equal to A inverse B. So, that is very straightforward actually. So, there is nothing there actually. But A inverse is always possible because determinant of A is not equal to 0. A is a non-singular matrix. So, that is a unique solution, and you have seen that many times actually already. Now, the interesting case turns out if that matrix is really non-square, that means m is either greater than n or m is less than n. So, let us study first case 2, where m is less than n, that means it is actually under constrained problem. Remember, n is more, okay. N is more means number of variables are more, and m is less means the number of equations are less actually. Okay. That means really it is an under constrained problem, you have more free variables to satisfy this equation. So, obviously, you will have infinite solutions actually. Okay. So, out of these infinitely many solutions, You can try to find a solution in various ways. You can I mean sometimes we force some of the components to 0 and then tell okay we will enforce that those components to 0 and find out a solution for rest of the things, that is possible. One other way of telling that okay let me find out a norm minimizing solution actually. That means I want a solution which will satisfy this equation exactly, but on top of that it will also minimize this second norm of this vector actually. That means if I take the distance from origin, the distance is going to be minimum actually. Okay. Yet I will satisfy this equation exactly, remember that there is no approximate satisfaction, this equation will always be satisfied actually. So, the solution happens to be, I mean if you really carry out this optimization and things like that, the solution happens to be nothing but a pseudo inverse B, where the pseudo inverse is defined, the right, it is called right pseudo inverse by the way, it is defined something like that. Okay. And then the details and all you can see matrix theory by Ortega, I mean that is a very nice book actually. You can see some of these things there actually, many of these concepts I have taken from there, okay, from that book actually. And then this solution happens to be a right pseudo inverse. If you apply with this formula, then it is nothing but that solution actually. And remember, this solution will exactly satisfy this equation. Okay. That means you are not compromising the solution nature actually. Solution is guaranteed. On top of that, I am getting a little more actually. Okay. And this concept will be useful to us later when we talk about optimal dynamic inversion. Okay. That is where we will also formulate a norm minimizing solution for the control variable. You will have more control variable than necessary. Okay. Then you will have a formulate a problem where you want a solution which will satisfy the equation exactly. On top of that, you will have a control minimizing solution actually. Okay. So, those things will be needed later actually. So, this is the concept where you can see that okay, I can get a solution which is also minimize this, which can also minimize this cost function actually. So, that is the solution that I am talking. Now, what about the next case? That means if the other case happens, that means the number of equations are more than the number of free variables. Obviously, we are talking about a over constrained problem. Okay. The free variables are less, the number of equations are more actually. So, unless some equations are a linear combination of the other equation, then in that case you can eliminate that equation. But if you assume that none of the equations are having that property, that means all the equations are justifiable linearly independent decoupled equation like that actually, then you are caught with a situation where you cannot find an exact solution, because all the equations you cannot satisfy all the time actually. So, a very natural way of asking that the next question is, can I find some solution which will satisfy most of the equations in an approximate way, all of the equations in an approximate way actually. That means, if you talk about pictorial idea sort of thing, suppose you have two lines, then obviously the solution is the point actually. Now, if you have 3 lines, the third line need not pass through that, it can pass through something like that. Okay. Then you are trying to find out a solution which will be close to all the 3 points actually, whatever 3 points you talk about, right. Each of the solutions, suppose this is let us say this is L1, this is L2 and this is L3. So, obviously, L1 and L2 has a solution, this is L1 and L2 solution, this is L2 and L3 solution, then this is L1 and L3 solution. Okay. We are not interested in any of that, rather what we are telling is we will find some solution which will very close, I mean which is rather close to all of them actually. Okay. So, in that sense we will tell okay, we will let us go ahead and minimize this particular quantity Ax minus b, second norm of that, we will try to minimize that quantity directly. Remember, this cost function is different from this optimization problem. Here we want to minimize the norm directly subject to this constraint, but here you just want to minimize this one as a free optimization problem, there is no constraint actually. Okay. And interestingly, this also happens to be a pseudo inverse solution, where the pseudo inverse this time is defined like this, and this is called as left pseudo inverse actually, it is not right pseudo inverse anymore. And right. So, the solution formula, if you see, this is right pseudo inverse, this is left pseudo inverse actually. Okay. Now, this as I told, the solution need not satisfy the equation Ax equal to b exactly, however, it will satisfy all of them in an approximate sense actually. Okay. And it is also, I mean it is interesting to see that this equation can be derived from a different perspective also. Suppose you have Ax equal to b, okay, then you simply multiply both sides with A transpose, let us say A transpose A, x equal to A transpose b, and then you take A transpose A is non singular, let us say, then you actually x equal to A transpose A inverse A transpose b. Okay. So, this is nothing but the same matrix that you see here actually. Okay. So, that is also possible to do that, and there are dimensions. If you say vector space analysis and things like that, you are actually working in a reduced dimension actually. You are not talking in a original dimension, but you are working in a subspace, not the full space actually. Okay. Those connotations, those I mean implications are there actually. Now, what is okay? What is a pseudo inverse or a generalized inverse? It is either it is we are talking about a left pseudo inverse, which is defined that way, or you talk about a right pseudo inverse, which is defined that way. And all this both of the pseudo inverse will satisfy all of these properties. Okay. The very nice thing is, if A happens to be a square matrix and A is nothing but like A is non singular, then this pseudo inverse is actually an inverse, no matter what, whether you take left or right. If A is a square matrix and determinant of A is not 0, then pseudo inverse is actually inverse. That is why the name pseudo inverse comes actually. Okay. And then you talk about all other property what you see will almost feel as if it is an inverse. Suppose if you just take an inverse, let us say, so A inverse A is identity, so I left out with A, and similarly if it is A inverse A is identity, you are left out with A inverse. So, it will feel almost you are working with an inverse. So, that is why it is not really an inverse. Okay. This is a different formula, it is not inverse of A, but it is very close to an inverse actually. So, these are called generalized inverse or pseudo inverse actually, that is the property. This has its many uses. I mean we will see one of the uses, as I told, we will see that again in the optimal dynamic inverse when we talk about that, and there are other many things, but we talk this property is very useful in optimization problems actually. Wherever you see optimization problem, and if it is over constrained optimization or under constrained optimization, that is what typically it happens, then it happens to be like that is the requirement that it pops up actually. So, with that I will stop this class. Thanks a lot.